Okay, page 6 of math induction. So here's our conjecture. This is a little bit different than the ones we've done up until now. You can see that the initial value for n would be 1. So for the base case, what we're going to do is we're going to write if n equals 1, and then we are going to look at writing this for n equals 1. So let's see, if this was n equals 1, it would basically be this term by itself, right? Because if we put 1 into here and here, then that would be 1 times 2. So that would be this term here, okay? So if we had this term with 1 in it, it would be 1 over 2. And that would be equal to this. With n equals 1 in it would be 1 over 2. And yes, indeed, it's true. So P of 1 is true. Okay. Now let's go to the base case. So the base case would be this with k substituting for n. So let's do that. So if P of k is true, then we're going to put 1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over k times k plus 1 equals, and we're going to assume that that is equal to k over k plus 1, okay, just like it says there. Then we're going to do the k plus 1th case. So we're going to rewrite this, except now we're going to go all the way up to k plus 1. So first we're going to have 1 times 1 over 1 times 2 plus 1 over 2 times 3 plus ... And finally, we're going to have this second to last term, which is k times k plus 1. And then we're going to add finally the last term, which is k plus 1 times k plus 2 equals. And we don't know yet. We're not going to finish that up. We're going to try to make it look like this and substitute this in and see if we can make it true. Do you see how this is this? So let's do this. We're going to substitute in for here. We're going to put k over k plus 1. And then we're going to add that to the last term, 1 over k plus 1 times k plus 2. And then let's see if we can simplify this somehow and make it look like some version of this. First thing we're going to do is going to make a common denominator. So it would be k over k plus 1 times k plus 2. And we're going to multiply the top also by k plus 2. And then we're going to add it to 1 over k plus 1 times k plus 2. And then if we now we have the common denominator, k plus 1 times k plus 2. And on the top, we got k squared plus 2k. Do you see I just expanded that? Plus 1. Ooh, now look at the top. The top is a perfect square. K plus 1 times k plus 1. And the bottom is k plus 1 times k plus 2. Now I can cancel those two out. And I'm left with k plus 1 divided by k plus 2. That looks a lot like this, doesn't it? So before I had k over k plus 1, if I replace k with k plus 1, I'll have k plus 1 on top and I'll have k plus 2 on the bottom, which is exactly what I ended up with here. So I have proven the k plus 1th case. So thus 1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over k times k plus 1. I'm sorry, k plus 1 times k plus 2 is equal to k plus 1 divided by k plus 2. And that's true if the original case of 1 over k times k plus 1 is equal to k over k plus 1. Okay? And since P of 1 is true, and P of k plus 1 is true whenever P of k is true, then P of n is true for n is greater than or equal to 1. That's it for A. Let's go down to 4C. Okay, so for this case, our conjecture is prove that this expression is equal to this sum expression for n is greater than or equal to 1. Okay, so the base case is if n equals 1, then basically this expression here would be 1 over 1 times 2 times 3, which is the first term. It would just be that first term. So let's make sure that's true. So it'd be 1 over 6 is equal to, and then let's check this last one. If we put 1 in for all the n's here, we'd have 1 times 4 on top, 4. And on the bottom, we'd have 4 times 2 times 3. 4 times 6. Look, it's 1/6. So it works. So P of 1 is true. Now let's take the P of k case. So we're going to take the left side and we're going to substitute k in for all the n's. So that would be 1 over 1 times 2 times 3 plus 1 over 2 times 3 times 4 plus ... plus 1 over k times k plus 1 times k plus 2. And we're going to assume that this is true, that it's k plus 3 divided by 4, k plus 1 times k plus 2. So we're going to assume that's true. So now we're going to rewrite P of n, and now we're going to substitute in k plus 1 for all the n's. So the first term is still going to be 1 times 2 times 3, etc. And then there's going to be the kth term, which would be k times k plus 1 times k plus 2. And then we got the k plus 1th term, which would be k plus 1 times k plus 2 times k plus 3. And that, we're going to see what that equals to, okay? But remember, the strategy is always we're going to try to take this expression here and find it somewhere here and substitute with that expression. So let's go ahead and do that. We're going to put the right-hand side expression over here. And so we're going to have k over k times k plus 3 divided by 4 k plus 1 k plus 2. And that's going to be added to 1 over k plus 1 k plus 2 k plus 3. And let's see what that equals to. Well, as usual, we're going to try to put it over a common denominator. So the left side, we're going to multiply the top and bottom by k plus 1, and the right side, we're going to multiply the top and bottom by 4. So let's see, the left side is going to have k plus 1, k plus 2, k plus 3 in the denominator. And the top is going to be k plus 3. So it'll be k times k plus 3 squared, because we're going to multiply an additional k plus 3 to make a common denominator. And then the right side, we have to multiply the bottom and the top by 4. So there's going to be a 4 on top. Let's see. Now, if we combine that, it would be, let's see, this part here would be k times k squared plus 6k plus 9, right? And if we multiply it times k, it would be k cubed plus 6k squared plus 9k. And then it would be plus 4. So let's put that. We're going to put k cubed plus 6k squared plus 9k plus 4. And then the common denominator is 4 times something times something times something, right? Let's use the calculator and maybe see if this is a factorable equation. So I put it into polysmlt and I found out that this is factorable. It's k plus 4 times k plus 1 times k plus 1. And remember, the bottom of this is 4 times k plus 1 times k plus 2 times k plus 3. Is that right? Yeah, it is. So I can cancel this and this, and I'm left with k plus 1 times k plus 4 on top, and on the bottom I have 4 times k plus 2 times k plus 3. Is that what we wanted? So if we go back and look at the original expression, on the top we have k times k plus 3. Now if k is k plus 1, then it would be k plus 1 times k plus 4, so the top is perfect. What about the bottom? So we have 4, that's good. Instead of k plus 1, we have k plus 2. Yeah, if k is k plus 1, then k plus 1 becomes k plus 2. K plus 2 becomes k plus 3. Perfect. So this is exactly what we wanted to get. So if we wanted to write the expression here, what we could do is we could grab this here. We'll put it here. Make it small. Okay, and so this is equal to this. Let's get rid of some extra lines here. And then I'll make it small. Put it there. If the P of K, the original P of K statement is true. And the original P of K statement is up here. Okay, so this here, I'm going to put it here. Okay. So thus, this is true if this is true. And then finally, we're going to come down the bottom and we'll say if since P of 1 is true and P of K plus 1 is true, whenever P of K is true, then P of n is true for n is greater than or equal to 1. And that's the end of this page.